Hi everybody, so I'm Simon Bongocote from Polytechnique Montreal. I'm working in the team of Professor Eric Laurando, who's doing the keynote there today. I will be the chair for that session. So we'll have here three talks of 15 minutes plus 5 minutes of questions from three members of the CHIUW team at HP. And the first speaker is Michael Ferguson from HP, presenting planned improvements to the CHIUW compiler. So I'll let him talk.
All right. So I'll go right. You already know my name, so I'll carry on. You know what I'm going to talk about. So in this talk, I'm going to sort of go through the compiler improvements topic in these 4 sections. I'm going to start by talking about where we are with the compiler and why these improvements are important. I'm going to talk about the main missing features that are hard to do with the compiler we have. I'm going to talk about a proposed direction that will involve some architecture adjustment to the compiler, and then I'll finish up with some progress in this direction. So where we are with the compiler today, we have a compiler, but we have some problems with it. The most obvious is that it's pretty slow. It takes, depending on your configuration, 5-7 seconds, something like that, to compile even the simplest program. And then for a large program like Arcuda or probably something of the size of Champs, it will take minutes, 10 minutes, 15 minutes, something like that. So we have something to do to try to improve that. And then we have some issues within the compiler in terms of how the compiler is structured and how it represents programs. The main issue here is that the compiler is structured only for whole program analysis. It's architected in a way that makes it difficult to add separate or incremental compilation. And then related to that, it's unclear how we could integrate an interpreter or add IDE support or do something like support an eval function for chapel snippets. So we'll talk more about those in a second, but the way that the compiler's sort of whole program is a big impediment there. And then the last category here is that in terms of development, we could do better with the modularity of the compiler implementation and having it be sort of more library. And when a new developer comes to work on the compiler, there's a pretty steep learning curve and it takes a long time. So we'd like to improve that also, but as it is, right, if we have a team of developers who've worked on the compiler for a long time, it's not that big of a deal. But if we want to include more community members or bring up new compiler developers faster, then it's an issue. So those are I just talked about some of the problems with the compiler, but the compiler has done well at, I think, its primary goal of supporting the evolution of the Chapel language. And then beyond that, it actually does reasonably well at optimizing programs. We have some key optimizations that some of the other speakers will talk about. And then the compiler is pretty fast to build. It's relatively portable itself. And then we have some other parts that are separable from the compiler. The internal and library modules are separate for the most part from the compiler. And we have a lot of modules. Like Brad said, we're working on stabilizing them, but that's a different effort and doesn't need to be tied to the compiler. And then we have a runtime library. That's what we call the C code that helps Chapel programs run. And that's got pretty good architecture and it doesn't need any major changes right now. So that's also sort of separable from this compiler effort. So on this next slide, I'm showing sort of a table of the passes and in some cases groups of passes that the compiler runs when it's doing this whole program compilation. So actually the compiler has 41 passes, but I'm not showing them all here. I've sort of collapsed some into groups. And then each of these passes will run for all of the program and do that process, whatever it is that the pass handles, before it can move on to the next pass. So it's, like I said, it's a whole program architecture, and each pass is whole program. So besides the pass list on the left, you can kind of see the columns there. I have the time for hello world, which is meant to represent a small program, and the time for Arcuda, which is meant to represent a big program. And you can see that even for hello world and Arcuda, in both of these cases, the resolved pass and the make binary pass are sort of the long poles in the tent. And then over on the right, I have an approximate size in terms of the number of lines of code in the compiler itself implementing these passes. So you can see that the resolve pass is actually a relatively large part of the compiler. And yet, like I said, it's one of the long poles in the tent in terms of speed. So we're looking at how to improve on this situation. But this is shows a little bit of the context. Okay, so in terms of missing features, the main missing features that people are regularly asking for are IDE support beyond the very basic syntax highlighting that is relatively easy to support with other tools, and separate or incremental compilation, or more broadly, just make the compiler faster, right? So for IDE integration, we need the compiler to behave more like a server. It's going to get some kind of limited query like, oh, complete this thing the user typed, or what should I show the user when they mouse over this thing? And we have to answer that quickly. The IDE experience won't be very satisfying if each one of those questions takes 7 seconds to answer. And then incremental and separate compilation, to implement those, we really need some kind of compiler structure that is more flexible than this whole program per pass kind of thing we have going on right now. So what the next part of the talk is going to be about is compiler architecture improvements that we're planning to make these problems easier to solve. So here I will get into that. So in this picture, I'm showing the sort of a picture of the compiler architecture we are trying to move to. So on the left side, there's a label of responsive compiler, and that's named after an idea from the Rust community that I will get into in a minute. And then on the right, there's a part that is different and uses progressive lowering. So kind of going from left to right, our compiler starts with some source code, it parses it, we'll parse it into some mostly immutable AST. That's not what we have today, our AST is mutable. Then it will run a resolution process. Recall that was one of the longer time operations. And the resolution process will result in the AST we have that's mostly mutable, and then also some maps indicating the result of resolution. Then we're going to take that combination and we'll lower it into a different AST or IR. Here I labeled it mid-level IR. That IR is going to be mutable. That's going to support progressive lowering. So when we can do things like optimizations where we modify the code representation in place when we do the optimization. So at a really high level, this design is kind of along the lines of a bunch of other compilers. They don't all necessarily follow this exact story, but they do have some of the elements. They have a different representation for AST than their mid-level IR. They have progressive lowering at some point in compilation. And then this early point of the compiler that I labeled responsive compiler here, that's the part that's really relevant for IDE integration. And additionally, it's the part of the compiler that does the most interprocedural analysis, which is really relevant for how we can do separate compilation. So we need to make that responsive compiler part really incremental. So in order to get to achieve this picture in the implementation, we'll sort of go through these steps at a really high level, right? We'll make the new AST that's mostly immutable. We're trying to make this AST more faithful to the source code for the early passes. We'll make a new pass architecture that's got less rigid ordering. In particular, is mostly processing things at a function at a time. And we'll convert our new AST into the old AST so that we can sort of divide the problem of updating the compiler into two halves, right? We have a new part and then we plug it into the old part, and then we don't have to rewrite everything all at once. And then gradually over time, we can port the later passes over to a new intermediate representation that's more suited for optimization than the current AST we have. So on this next slide, I'm going to talk about the responsive compiler idea. The responsive compiler, at least as far as we know, is something that we learned about it from this talk from Nico Matsakis, who's a Rust compiler developer. In the talk, Nico presents a vision of good IDE support that's really incremental and demand driven. It's fast. It just processes enough to answer a query. So you can imagine somebody sitting at an IDE, they start to type in like new block array, right? And then we can hit new block and hit tab and see the different ways to complete that. And like I said already, in an IDE context, having fast response times are really important for the experience to be satisfying. In this talk, Nico goes into some details of the strategy and what it relies on. The idea is to structure the compilation in terms of lots of fine-grained queries. So a query might be, for example, asking what is the type of a particular variable. Then there is a framework for these queries that manages the dependencies among the results. And each query saves its result, and it's going to be rerun only when necessary when the input is updated. So it's a very incremental framework. For example, if the source code didn't change at all, then we don't need to rerun a query that is computing the type of one of the values. If part of the source code changed, but the part relevant to that variable's type didn't change, then we shouldn't need to do very much recomputing either. It's important for this idea that the query results are separate from the input. So in the current production compiler, we do most of the process of compiling by modifying the AST in place. But that doesn't work very well in this context of trying to save results, compare against the old result, update things, and that sort of thing. So instead, we have this immutable AST, and then we'll have maps to save the results of these different queries. And then in Nico's talk, actually, he goes into a fair amount of detail about how there's AST IDs that support these maps. So here are some example queries that this framework can support that we'll probably have in something along these lines in our compiler, right? So first, you might have something that takes that parses a file, so you give it a path and it produces some AST. If the that one's a little different from some of the others because you might need to read the file again every time you run the query to make sure it hasn't changed. Then you might have a query locate that takes some AST and then gives you the line and column number, because if we store the line and column number in the AST, then we'd have to recompute it all if you added like a new line at the top of your file. So we can store that separately in this kind of query, so we don't have to do that. And then these bottom four queries are sort of getting to how would we implement resolution. So you can ask for the symbols with a particular name, which ones are visible from a particular place, what are their types, and from there you can get to figuring out what a call might refer to. So with that, here's sort of a summary picture of the proposed architecture. And I'm going to note just that we're calling the new AST UAST for untyped AST. And then we're going to convert that into the current AST for now, but at some future date, we hope we might be able to use MLIR for the rest of the compiler. So now on to the last section of my talk about what progress we've made on this effort so far. So first of all, we are developing the new compiler code as a library. As part of being a library, it's good to have some documentation for people using the library. So we've wired up some documentation generation with docs comments into our documentation pages. And we think that it being a library and having documentation will be really meaningful and allow community members to contribute chapel tools. And that's important for us because, as Brad said, for example, right now we're not really doing a lot with, say, performance tools, but maybe you would like to investigate how you might be able to write one of those that's aware of chapel syntax. So some library use cases for this library besides the compiler itself are maybe a linter or a documentation tool, and then obviously IDE integrations. On the next slide, I'm showing
Michael, it's been 15 minutes, so if you want to wrap up.
Yep, I have just this one slide and then it's questions.
Good.
So on this slide, I'm just showing an example of something that is working right now. We're partway through implementing this untyped AST, parsing it and translating it to the old AST, and we have demonstrated some incremental recompilation. That's what this is just showing, some of the kinds of things we're parsing and representing in AST right now. So on the left, there's just an example program, and then on the right, there's our test program that can, we can modify that file and then incrementally parse it again as a way of exercising our framework. Okay, now I'm ready for questions. Thank you.
Thanks, Michael, for the talk. So first question is from Tiago Carneiro. Are you planning to provide more precise hints to locate the syntax errors?
Are we planning to provide more? I might be able to see
precise hints to locate the syntax errors.
Right. So we do realize that better error messages is that's an important goal of our sort of efforts on improving the compiler. I didn't go into that very much in this talk for time reasons. We are trying to get column numbers into the error messages, and we are trying to get to a point where we can produce more error messages in a single run. As far as individual error messages, it depends on which one it is. For syntax errors specifically, we are still using Flex and Bison, and we've made some efforts to try to get decent error reporting out of Bison, but I think we might need to use a different parser technology to do a lot better there. So I wouldn't expect that syntax errors specifically are going to be really different in the near term, but I think it would be reasonable of us to switch to a different parser that's better at that at some point.
Okay, next question from Akiro Ayashi. Is asking if the compilation time numbers were obtained with the LLVM backend enabled, and is curious to know how it affects the compilation time. I guess it refers to our CHIUW.
Yep, right. So the answer is that yes, those ones I showed did have the LLVM backend enabled. For the Arcuda times I showed, it's compiled with -- fast, so optimizations are running, and that's part of the reason why the make binary step took quite a lot longer. And generally speaking, at least on some systems, we see the LLVM compilation, if you're not doing optimizations, being faster than generating C and compiling with a C compiler.
Okay, there's another question from Mike Merrill. Is a direction to compile correct code and incrementally compile a more optimized version?
I guess I'm trying to understand the question. I think that the question is asking if we would allow compilation of a program without optimizations on, and then compile it again with optimizations on, and benefit from some of the work we did in that compilation. I haven't really thought about that yet. So that's not something we've been thinking about so far, but certainly when we get to having an incremental compiler you would be able to benefit from earlier compiles with optimization if you're doing a new one with optimization. For the early parts of compilation, though, I think it would be reasonable to share a lot of the, for example, resolution information. For the most part, shouldn't change if you have optimization on.
I think we have time for at least the last question from John Hartman. Will this incremental approach affect the quality of the resulting binary?
So I'm not expecting that we will produce significantly different code at the end of the day. There are a couple of ways that we do expect to have better code because we're planning to add fewer temporaries in the new compiler strategy. It is possible there will be some case where adding more temporaries ended up making the generated program go faster, but I think that would probably be more anomalous. But anyway, we do have lots of performance graphs that we do, so we will watch for that kind of thing as this work progresses.